Hey guys, so this is going to be a quick video going over how to solve these FRQs that we talked about in our Google Meet. If you were unable to attend the Google Meet session, I'm hoping that these videos will help us to better understand how to solve those problems. I couldn't record the Google Meet session and share it with you because students responded and we had a conversation, which is exactly what I want, so please don't stop doing that on the Google Meet meetings. But I'm just going to go ahead and do this here myself to show you guys who weren't able to attend. So what we're going to do is we're going to kind of walk through and talk through some good ways to approach an FRQ like this. It's a data-based FRQ, which is going to be one of the types of FRQs on the test on your digital exam. So let's go ahead and dive right in. And the first thing we're going to do is read carefully through it, and I'm going to grab a pen so that I can go ahead and mark important words. So a student conducted an experiment to determine the molar concentration of solutes in chicken eggs. Now the first thing I'm going to underline is solutes and molar concentration. So a big part of this is kind of remembering associations. And if I'm remembering correctly, when we talked about molar concentration of solutes or solute concentration, which is a big word here, then we were talking about tonicity. So I know this has got to have something to do with tonicity. Eggs were soaked in vinegar to remove the shells. The eggs were then placed in sucrose solutions of different concentrations. Okay, so we can see here that they're actually different concentrations, and that I'm going to go ahead and underline. The data is shown in the table below. So here we see the sucrose or sugar concentration of the solution we put the chicken eggs in. Here's the initial mass of the eggs in grams, the final mass in grams, the change in mass as the chicken eggs were exposed to different sucrose concentrations, and the percent change in mass as the chicken eggs were exposed to those concentrations. Now, why did I just go over the table like that? Well, basically, a good way to approach a database problem when you're given a chart or a graph is to just kind of talk your way through it, just like I did. So I explained to myself what I was seeing. I tried to put together the logic of what they were doing in their experiment so I could understand what was happening. And then I was able to read this whole thing and kind of get an idea of their study. So from what I'm seeing, they put a bunch of chicken eggs in different concentrations of sucrose, and they saw that the mass of the chicken eggs changed. Before I even draw a graph, I can see that with a 0 molar concentration of sucrose, the chicken egg actually increased in mass. So it changed in a positive value, which means that it got bigger. Whereas in all the other sucrose concentrations, the egg seems to have shrunk or changed in mass somehow. Interesting. Okay, so now I go into the questions. Using the most appropriate data, construct, aha, a bolded word. So a bolded word is going to mean that there are point values associated with that word. Okay, so I know that one of my points, at least one of my points, is going to come from construct. So using the most appropriate data, construct a labeled graph on the axes provided below to best illustrate water movement into and out of the egg. Now, I didn't have space to put the axes below, so you would, normally they would give you some axes, but I didn't have space to do it. To best illustrate water movement into and out of the egg, explain, here's another bolded word, why there is a difference in the percent of mass change of the eggs in the different sucrose solutions. Okay, so let's go ahead. I'm going to go ahead and also underline best illustrate. Let's go ahead and see if we can figure out the best graph to use. I'm going to go to a different page here so we can see. Now, if we're going to draw a graph based on the experiment, there's a couple of things we need to identify. The first thing we need to identify is what the independent and dependent variables are, because we need to know what to put on our axes. So I'm going to go up here and I'm going to try to determine, okay, what is my independent variable? What are the researchers changing that's causing a change in the egg? Okay, so the researchers are changing, the molar concentration of sucrose. So that is going to be my IV. Typically, I'll see it over here on the left-hand side, but it's not always. And I'll try to see if I can figure it out based off of the experiment and my understanding of it. Since I know that they changed the sucrose concentration to see how that would affect the egg, this is my independent variable, and I know that the change in the egg's mass, what happens to the egg, is my dependent variable. Now I could also use the percent change in mass, and because I know what the scoring guidelines for this problem are, that is also acceptable. But I'm going to go with the change in mass in grams just because, what the heck. Okay, so now I'm going to go ahead and draw the graph. Now here's a little tip with drawing the graph. So now we know what goes on our x and y axes, but we have a weird y-axis. it's not all positive values. Some are negative, some are positive. So to best represent that, what I would recommend doing, even though you could do your typical L-shaped axes, I would do an axis setup like this. What this allows you to do is this allows you to put the 0 point of the graph right there, or the origin, right there in the center of the graph, if I could get it to line up properly. Meaning that anything below that is negative, anything above that is positive. It's a great way of building a graph that can show a change from positive to negative values. Okay, then I would have to go ahead and put in my increments. Now, because I'm working with positive and negative values, my highest one is 3, around 3. My lowest one is around -10. I might suggest going up by, 2s, or you could go up by 1s. I'm going to go up by 2s. So each one of these tick marks will represent 2. So 2, 4, 6, and that's above what I need really. And then down here, 2, 4, 6, 8, 10. Now I could have spread these out a little bit more, but right now just sort of a rush job. That'll do. So then we need to add our increments down here. So that was our y increments here. We need to have 0, which I'll just make along the origin, 0.5, 1, and 2. So I'll go up by 1. So we have 1, 2, and we'll go ahead and say that this right here is 0.5, and this is 1.5 for reference, even though we don't need it. Okay, so now we can go ahead and plot our points. So at a sucrose concentration of 0, the change in mass is about 3.2. So at 0, we go up, so 2, and this would be 3, and this would be about 3.2 right here. Okay, so at 0.5 for sucrose concentration, it's -1.6. So 0.5, I'll go down 1.6 is probably right around here. Okay, 5.61, -5.61 for 1, so I'll go to 1, and then 2, 4, and 5.61 is going to be just before we get to 6. And then we're going to have 10.35 down here, so this is for 2, so we'll go all the way down, 2, 4, 6, 8, 10, and it's just beyond 10. Now, I'm not doing this to make it perfect in any sort of way. I am just trying to illustrate this, so, oftentimes with these FRQs, there's a time limit, so I would suggest trying to be careful about how much time you spend doing any one thing. Okay, so I end up getting a graph that looks something like this. Now I'm not done because I still don't have any of my axes values in place, or units and labels. And I would typically do this before even drawing the graph oftentimes, so I'm just doing this out of order right now. But what I would do is down here you would say sucrose concentration in grams, and then over here we would have our change in mass, also in grams, which is nice. And then our title for the graph, could be the effect of sucrose concentration on the mass of eggs. And that gives you a pretty great solid graph to work with. So now what we can do is we can sort of interpret this graph and see if we can figure out what we're being asked. So for A, we constructed our labeled graph and we best illustrated the water movement into and out of the egg. Explain why there's a difference in the percent of mass change of the eggs in different sucrose solutions. So this requires us to go back to thinking a little bit about tonicity. Okay, so if you guys remember, there's 3 conditions that we can have in tonicity. There is isotonic, hypertonic, and hypotonic. Hypotonic, which I'll draw over here, hypotonic means that you have very little solute outside of your cell versus inside of your cell. In other words, the inside of your cell has a much higher solute concentration than outside. If you remember, water likes to follow solute, right? So this affects the water potential. Remember, pure water has a very high water potential, whereas water mixed with a lot of solutes has a very low water potential. So the inside of the cell has a lower water potential than the outside. And because water likes to diffuse passively through osmosis from a high to a low water potential, we are going to see water enter into the cell, and the cell will expand in size. The hypertonic is going to be exactly opposite to that. So our that's a weird looking cell there. Our hypertonic is going to be exactly opposite to that. So what's going to happen here is that we're going to have more solute outside the cell than we'll have inside. Because the solute potential is higher on the outside and the water potential is lower on the outside and higher on the inside, water will flow from high to low and water will actually exit the cell. So in this case, we see the cell shrink. Isotonic is the medium right here. It's going to be an equal amount of solute concentration outside versus inside the cell. And that's going to mean that there's no net flow of water. We can show that in a lot of ways, but one of the ways we show it is to show an arrow going out and an arrow coming in to show that there's water moving still, but it's not actually moving more out or in. It's equal between the two. So there's no change or net change in the cell at all. So how does that relate to this graph? Well, as we can see, the egg grows when it is at 0 sucrose concentration. And it begins to shrink as soon as we start adding a certain amount of sucrose. So this line is showing us the growth of the egg. Up here, since it's growing, we can assume that any positive value of this graph is going to represent the hypotonic solution. So in other words, the solution has less solute than the egg. Anything beneath that 0 line is going to represent the egg when it is in a hypertonic solution. Any point at which the graph or the line intersects the x-axis at the 0 line, we can assume that that means that the egg and the solution are isotonic to one another, containing the same molar values for their sucrose concentrations. So what I would recommend putting for this answer then is the answer that we came up with when we were doing this problem together. So I'm going to go ahead and copy and paste that in. Sorry. So as solute increases outside of the egg, the mass of the egg gets lower because the water will leave the egg traveling towards the area of higher solute concentration. As solute concentration decreases outside the egg, the mass of the egg gets higher because the water will enter the egg towards a higher solute concentration. You could also explain this in terms of water potential or water concentration. Okay, so B, using the data, determine the molar concentration of the chicken egg cytoplasm and justify your answer. Basically, this is asking us, okay, so what exactly is, so how much sucrose is in the chicken egg, basically? And we have two points here. We need to determine the answer and then justify it. So how do we determine how much sucrose is actually within the egg? Well, if we're only given the molar concentration of the solution itself, that might seem impossible. But remember, when this line crosses the 0 axis, that means that there's an equal amount in the solution and in the egg. So actually, whatever point this is right here, where it crosses, has to be the amount of sucrose in the egg. And since this black line represents 0.4, this would be somewhere between 0.3 and 0.4, or 0.5, somewhere around there. And that is how much sucrose concentration is in the chicken egg. It's as simple as that. All right, so we go in and we grab this one right here, and we copy, and we bring it back over here, and we paste. The molar concentration of sucrose in the chicken egg cytoplasm is around 0.35. This is an arbitrary number I picked around about there, because that's the sucrose concentration where the line of the graph crosses the x-axis, or the line of isomaticity, which basically means that the egg has got to have the same amount of solute as the concentration of the solution. I hope that makes sense to you guys, all right, and that's the first little bit of that problem. So that's how I would solve that. If you guys have any questions, please let me know. Okay, and then we get to our second FRQ. So trichomes are hair-like outgrowths of the epidermis of plants that are thought to provide protection against being eaten by herbivores. In certain plant species, stem trichome density is genetically determined. So basically, that's, if I'm explaining this to myself, you know, some leaves look kind of hairy. That must be what they're talking about. Those trichomes must be the hairs that protect the plants, because who wants to eat a hairy plant? To investigate variation in stem trichome density within the plant species, a student counted the number of trichomes on the stems of 6 plants. Okay, so then I'm going to start underlining stuff. So they counted the number, I'm going to underline this, they counted the number of trichomes on the stems of 6 plants in 3 different populations. Why am I underlining that? Well, because it's going to help me to understand sort of how they outline their experiment. When you're trying to read an experiment, a description of an experiment, whether it's data or what have you, your goal is really in your mind to try to be sort of reproducing that experiment in your head and figuring out how they put it together. So here I can see they had 3 different populations, and they took a sample of 6 plants from each of those populations to figure out, the variation in the number of trichomes. So the student used the data to calculate the mean trichome density, so the number of hairs per square centimeter, and the results are provided in the table. Okay, so I can see here's my populations. Here are the individual plants. I'm actually going to mostly ignore those because I'm really interested just in the sample mean and the standard error of the mean, because they already calculated the mean for me. I don't have to worry about calculating it here. So based on the sample means, I need to identify, there's one point, the 2 populations that are most likely to have statistically significant differences, that's a big thing, in the mean stem trichome densities, and I need to justify my response. So 2 points there, and we're going to be looking at some statistical stuff. Okay, so let's go ahead and dive in. Well, the first thing, I need to identify populations that are statistically significant. What does that mean? Well, it means that when I use some sort of form of statistical analysis, in this case, such as the standard error of the mean, which is given to me, I'll be able to tell whether or not the differences in the means of these populations are most likely due to error, or, in random sampling error and chance, or because there is like a statistically significant difference between them. So in other words, if I was to compare these 3 means for these samples, 9, 11, and 14, okay, 9 and 11 are pretty close to each other. And so is the difference between these guys, like, is it significant that these guys have a mean density of 11 and these guys have a mean density of 9? Or did I just happen to select plants that gave me a slightly higher number in this one and a slightly lower number in this one? And if I did it again, I would find that they were swapped or reversed, or actually not, there's no real difference between these populations. That's what I'm trying to say, is a statistical test will tell you whether or not the difference between 9 and 11 is something you need to pay attention to, it's an actual pattern in nature, or if it's just some mistake that you made when you were collecting your plants. It happens. Okay, so how do we determine that using the standard error of the mean, and what is the standard error of the mean? Well, to remind you, the standard error of the mean is just basically saying, okay, so is the difference in my population means or my sample means due to random error, or is this an actual trend that I see in nature, just like I just said? The bigger your standard error of the mean is, that means the less likely it is that it's an actual trend in nature, and it's more likely that you just screwed up somewhere. But the smaller the standard error of the mean, typically the more reliable your data represents the actual population mean, which is really what you're trying to strive for. So I'm going to show you how standard error of the mean is applied to a graph, and this will help us to analyze our results. So I made a simple bar graph, population 1, 2, and 3, and then 5, 10, 15, and 20 is going to, I didn't do my units, which is poor of me, but that's going to be the sample, to represent the sample means. I'm going to guess the sample means are what? Number of hairs per square centimeter? Yeah, so that's what that stands for. That would be my units if I wrote them in. But I'm feeling a bit lazy now, and I don't want the video to take a long time, so for your sake. So let's go ahead and get started. So if I look at population 1, okay, so, and actually I added in, I drew this sort of, I drew over a little bit of this, so let me go ahead and add back in these purple lines. That'll make more sense. Okay, so when I made my bar graphs, for number 1, I was told that I had a mean trichome density of 9. So I took it up to 9 and brought it back down. For 2, I had 11. Went up, took it up to 11, this bottom green line, and took it back down, and then I went up to 14 for 3, because that was what the data told me. But it told me I have a standard error of the mean of 1. Okay, well, the thing about the standard error of the mean is it's plus or minus whatever number it gives you. So it's plus or minus 1. Basically, it means that if I was to go to the very top of this line, which was supposed to be 9 in the beginning, that's my sample mean. Okay, my error is, it's either 9 or 10 or 9 or 8, but there's one error up or down from the unit I got. So am I sure it's 9? No. It could be 10 or it could be 8. I'm not really sure, but the mean of trichome density is somewhere between 8 and 10. I went ahead and said 9 as the mean, but the standard error shows me that it could be either or. Okay, so this means that really this bar graph can fluctuate. It could either be shorter or it could be taller, as indicated by the second blue line. Okay, so if you interpret that for each one of these, right, this guy could be either 15 or 13, this guy could be either 12 or 10. Uh-oh, well now we have a problem, because if this guy could be 12 or 10, well, if it could be 10 and this guy could be 10, is there any real significant difference between 1 and 2? No. There's absolutely no, because the error bars overlap. That standard error of the mean makes it so that there's no statistically significant difference. These bars could actually be the same height. We don't know whether it's a sampling error or an actual, difference between these two populations. So we can't be sure about the differences here. But even with the standard error of the mean built in up here, there is no statistically significant overlap between population 3 and population 2. And there's an even greater chance that there's no overlap between 3 and 1. See how far away those black bars are from aligning with even the lowest of the error bars on population 3. So if I was to go in and put an answer here, I would say that the two populations most likely to have statistically significant differences in the mean would be populations 1 and 3. To justify my response, I would say the error bars do not overlap, and there's the greater distance between the highest point of the error bar in 1 and the lowest point in 3. Okay, and I believe we also did that one as, yep, okay, so we went ahead and came up with that answer as well. I'll go ahead and just paste it in, and voila, there you go. So populations 1 and 3 are more likely to have statistical differences in the mean stem trichome densities because their error bars do not overlap. The differences between bars 1 and 3 are greater than between bars 2 and 3. All right, so I hope this made sense to you guys and you enjoyed this FRQ practice. This is the first practice of many, so I look forward to working with you guys on more just like it. All right, guys. Hope you're doing well, stay safe and well, and I can't wait to see you next lesson. Oh.